My name is Miles, and I'm an early career fellow at the Collegium Helveticum at the ETH Zürich in Zürich, Switzerland. Today I'll be talking to you about some very early work towards developing comparative metrics for ranking the relative difficulty of achieving and sustaining spaceflight from different environments and within different environments. So in the first case, from simply getting from the surface of a planet to orbit, and in the case of planetary systems, just moving from the homeworld to the next nearest neighbor planet. The motivation for this project really came about from the realization that many of the technosignatures that have been proposed to date rely on the emitting civilization being spacefaring and having capabilities of orbital spaceflight, interplanetary spaceflight, or interstellar spaceflight. So in the case of orbital spaceflight, this might be a technosignature like the Clark exobelt. In the case of interplanetary spaceflight, it might be something like a Dyson swarm. And in the case of interstellar spaceflight, it might be something like a warp signature. But here I'll just start by talking about how we can get from the surface of a planet to orbit and the delta V that's required to do that. This is something that can be analytically calculated through the vis-viva equation, assuming perfectly impulsive maneuvers and no losses. However, as I'll show, this is not a realistic way to calculate the total delta V required to achieve orbital spaceflight. And so if we want to actually do this in a meaningful way, what we actually need to do is calculate the delta V of a realistic launch vehicle trajectory, including gravity losses, steering losses, and drag losses. Now, what's interesting is that drag losses are not actually particularly important, or at least not of a large magnitude when we get an optimal trajectory. But what does turn out to be relatively large is the gravity loss and steering loss. And the reason for this is because the atmospheric thickness of a planet tends to determine what is the maximum velocity that a launch vehicle can sustain through the lower atmosphere, given a particular limit to the dynamic pressure that it can sustain. And so what you see here is a plot of the maximum velocity possible in the lower atmosphere for different planetary masses on the x-axis, and the curves are different atmospheric mass fractions. And for reference, Earth's atmospheric mass fraction is roughly 10 to the negative 6. So what you can see here is already at 10 times the current atmospheric thickness of Earth, we start to run into serious problems where the maximum allowable velocity in the lower atmosphere is in the low tens of meters per second. And when we even go beyond that to still relatively minor atmospheric mass fractions, we're down to single digits meters per second, which makes it very difficult for any plausible trajectory to be reached. Now, if we actually run that for several different atmospheric mass fractions and planetary masses, we end up with the figure you see here. And what you'll notice is that the delta V required in a realistic scenario scales relatively as you would expect with planetary mass, but the atmospheric mass fraction is a multiplier on top of that as well. And you'll see that there are what appear to be missing points, but actually these are just points where the optimizer cannot find a physically plausible trajectory. And so part of that is an issue of the optimizer not converging, but at the same time, it is a good indication that this is very, very difficult to achieve in terms of getting off the planet and through such a thick atmosphere at such low velocities in the lower atmosphere. Now, in addition to getting from surface to orbit, the next milestone is just the most basic version of interplanetary spaceflight, which is, can we reach the next neighboring planet? And so in this case, what I'm showing is just the Hohmann transfer, coplanar transfer delta V required to go from the homeworld, which is the one sitting at the center of the habitable zone for its given stellar mass, and reaching the next neighboring planet, which is defined as being 14 Mutual Hill radii away, which is something that comes from the Kepler multi-planet data set. And in this case, what we see is that for larger stellar masses, they are much more energetically favorable to supporting interstellar transfers. And in addition to that, having lower mass planets that we're transferring between is also making it even more energetically favorable. So taking together, what we're looking at is lower mass planets with small atmospheric mass fractions tend to be favorable from getting to orbit, and higher mass stars between lower mass planets is more favorable for interplanetary spaceflight. And so that's a very early look at developing metrics for really ranking the comparative difficulty of achieving these spaceflight milestones, and getting to a point where we can apply this to the known exoplanets so that we can start targeting technosignature searches in an effective way. Upcoming research will focus on implementing realistic atmospheres. So right now I've used exponential isothermal atmospheres, which is an okay approximation for some things, but not great for others. So if anybody would like to collaborate on atmospheric modeling across very different rocky planet atmosphere environments, I would be very open to that. And also improving the ascent trajectory optimization code to really be able to push higher into the more massive planets and also handle higher atmospheric mass fractions, just to see how crazy we can get in terms of the extreme planets. And then also, of course, including planetary rotation, and for the interplanetary spaceflight, including some interesting dynamics there as well. Thank you for your time, and please let me know if you have any questions.